Hey everybody, this is a video for my Intro to Calc students, and this is our first video for Unit 2, where we are going to explore derivatives. So, we'll start with a very little bit of notes. In calculus, the derivative of a function is the slope of its tangent line or its rate of change. And you're probably looking at that and thinking, well, that's not a big deal. After all, we've been talking about slope and rate of change all through Unit 1. What's the difference here? Well, the difference is, the reason I put two dots is because I'm not quite finished that sentence. Let's start it again. In calculus, the derivative of a function is the slope of its tangent line, and I just realized that's the wrong its. It bugs me when I make grammar errors. The slope of its tangent line, or its rate of change, drum roll, expressed as a function in the same variable as the original function. I know that's kind of a long, rambly sentence, and at the start I had the wrong its, but see if you can kind of get your head around what this is saying. What we're going to do is we're going to express the derivative of a function as basically the slope of the function as it's changing. In other words, we're going to make an equation that represents the changing slope as I look at the entire function. Let me see if I can show you what I mean. I'm going to just go over to Desmos here for a sec. Here's our old friend y equals x squared, right? Think about this thing. So we've done lots of, we started with secant lines that approach the tangent, but we have a pretty good sense now that here's the tangent line, and notice its tangent point is making this line. Start thinking about the slope of this purple line. Well, for everywhere going up forever, this slope is going to be a negative value, right? Because the line's going down. Rise over run is definitely negative. Then when I go around the center here of the curve, the vertex, for a second there, my slope will actually be 0. Then my slope will be positive. Can you think of what a line would look like, or an equation would look like, that represented this slope as it was changing? It goes from negative, and you can see, as a matter of fact, I actually have the slope values over here. So right here I have a slope of about negative 3.4. If I go up, I have a slope of about negative 4. If the further I went up, the more steep it's going to get, so the more negative it's going to get. But as I go down here, it gets less and less steep, less and less negative, until again it's a slope of 0. 0, oh, get 0, 0, because it's a horizontal line. But then it goes up, and there it's a slope of 1, it's a slope of 2, it's a slope of 3, etc., forever. What would an equation look like that represented this changing slope? That's what we're going to find out. And we're going to find out by defining the derivative of a function. F of x, the function, or any function, has a derivative, f primed of x. And again, that would be a function. That would be the derivative of the function. Given a function f, the derivative of f of x, or sorry, given a function f, the derivative of f is the function f primed. That is not a 1. It is not an exponent of 1. It's actually like an apostrophe. It's a prime. You've seen primes before in math when you did translations in junior high, and it's possible you saw them when you had to solve for two different types of triangles in the ambiguous case of sign law. We don't like read lettering the triangle corners when we have a second case of the same givens, so we usually use primes. So prime is just basically an apostrophe. So the first function is f. Its derivative is going to be f primed, and it's defined by this formula. The derivative of x is equal to the limit as h approaches 0 of the function of x plus h minus f of x over h. This is the important formula. It should look really familiar. Isn't it very, very much the same thing we just saw in the last chapter when we looked at Formula 2 for a slope of a tangent line? Well, it pretty much is slope 2, but we usually call it, this formula is often referred to as the first principles of a derivative. And that's usually the way textbooks refer to it. So I'll give you a sec to catch up to me there. And we'll do some examples where we use our algebra to find derivatives, and then we'll kind of look at them on Desmos too, so that we can see what we're looking at. So we'll start with the one we were just looking at a second ago. Find the derivative for f of x equals x squared. So copy that down, please. And then, of course, we're going to use our new first principles formula. And there it is. So there's the formula. As always, we'll give you a formula sheet come test time. But if you got used to the formula 2 from the last unit, this should be pretty easy to remember. And okay, we plug in our values. So what's going to happen when we work with that? Well, I'm going to have to, I would say, expand that. So I'm going to expand this to the limit as h approaches 0 of x squared plus 2xh plus h squared minus x squared all over h. That's going to cancel those two x squareds. So that's the limit as h approaches 0 of 2xh plus h squared over h. Both of these things can divide by that h. So I have fixed the problem of when I put in my limit value, the denominator being 0, because the denominator doesn't exist anymore. And now I can actually plug in my limit value. Sorry, I'm off the screen. Now I can actually plug in my limit value, which is going to be 2x plus 0, which is equal to 2x. So I would say that f primed of x is equal to 2x. Interesting. So let's take a look again at Desmos. This time I'm going to look at this file. So there's the two things we just found out. We found out that f of x is equal to x squared becomes y equals 2x. By the way, Desmos can calculate derivatives and tell you, it won't tell you what the actual equation of the derivative is. We found out it was 2x. But you can see that if you actually say, hey, what is f primed of x? And Desmos will do that for you. Notice the green line and the blue line are, in fact, the same line. So there it is. Let's go to the other one again. So as this slope goes around, how does that slope make this green line? I mean, the slope is up here before, but wait a minute. Don't confuse the position of the point with the value of the slope. This green line represents the continuous value of the slope. And remember, we already kind of talked about this. Everywhere up here, the slope is negative. So it makes sense that on the graph, the green line's negative until I get to 0. Right? Remember that the slope at 0 is 0. So that makes sense that we cross the x-axis right there. And then everywhere going up this way, the slope is positive, hence the green line is positive. Maybe it would make sense, or make a little more sense to you, if I actually put the other line here. So give me a sec here. Suppose I put, there it is, and let's put a point on there to show that this is the value of the slope, right? So here, let's label it. So here, when I have an x value of negative 2.13, the slope value, the value on this graph is 4.531, but the actual value of the slope here is negative 4. So you can think about it. The rise over run here, rise over run is about negative 4 over 1. You can kind of see that if you make a little estimate here. And notice as the slope goes down, it's getting closer and closer to the slope of 0. And then it goes up. Cool. All right. Let's try a different example, shall we? Back to our page. And let's find, maybe before I leave this, I should point something out. Notice that the domain of this function is all reals, right? X is defined everywhere for x squared. You can put in negative numbers, positive numbers, rational, irrational, it doesn't matter. Everything gets squared and becomes a value. And notice that's also true of its derivative. 2x, the line y equals 2x, is defined everywhere, right? It goes forever in both directions. It has a domain of x as an element of reals. That won't be true of our next example. In our next example, we are going to find the derivative, f primed, if f of x is equal to the square root of x plus 2. Aha. What's that going to look like? All right, well, let's see. That's going to equal the limit as h approaches 0 of f of x plus h. So I replace the x with x plus h in this function. Then I repeat the function, and I divide by h. All right, what can we do with that? Well, there's no way we're going to make this h go away unless we perhaps rationalize that numerator. So a rationalizing we will go. And remember, this is our property of 1. We're really just multiplying this expression here by 1, so it doesn't change what it is. So this is the limit as h approaches 0 of, okay, I'm multiplying conjugates, so that means it's a times a, which is a squared, minus b times b, which is b squared. I'm going to put that in a bracket, though, so that I remember I'm minusing both of those things, which is together what the b value would be, all divided by the denominator. Now, the denominator, I'm not going to bother multiplying out. We kind of learned this last unit, that this almost never gets us anywhere. And at the end of the day, we don't really care what this denominator is going to be, because at the end of the day, if we can cancel this h somehow, plugging in a 0 for this h won't make 0 for the denominator. So really, this is the thing we have to kill. This is our target. And I can see we are about to kill it, because this is going to be the limit as h approaches 0 of x minus x plus 2 minus 2. Aha! The constant and the variable on the top are gone. And isn't that nice? So that means those h's are gone. So that's 1 over, and the denominator still has an h in it because I haven't switched over. I haven't actually applied the limit yet. Okay, let's apply the limit. So that's 1 over, and that's the square root of x plus 0 plus 2 plus square root of x plus 2, which is 1 over, now this 0 means this is just the square root of x plus 2, and this is the square root of x plus 2 plus the square root of x plus 2, so that's 2 times the square root of x plus 2. And that is f primed of x. Now, what kind of a thing will that be? The derivative of my first function was a nice straight linear equation. What the heck kind of a thing is that? Well, it's the reciprocal of a radical. And it's going to look something like this. Here is the original function, right? One of those radicals. It's basically a sideways parabola. And its derivative, notice, think about what's happening. Think about what's happening to the slope. Actually, let's go to the other one. Let's get rid of all these guys. Let's get rid of this. And let's make it the square root of x plus 2. Okay, so, oh, I didn't want you to see that yet. Sorry. Okay, so as the slope moves along here, oh, and that point there isn't right anymore. Oh, wait, that's not what I wanted to get rid of. Where's that point? What have I done wrong? Oh, no, that's right. Yeah, okay, I'll just hide that point. It's the right place. Okay, so here is, of course, the tangent line as it moves along. Notice it's kind of getting flatter because the steepness of the blue line is getting smaller, so the slope is getting smaller. But as I come in this way, what happens as I approach -2? Well, I have a slope value being calculated right there. Right now I've got a slope of 0.4, 0.5, 0.6, 0.7. There, I have a slope of 1 right there. I have a slope of 1.043, etc., etc. In fact, why don't I zoom in? Zoom, 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 zoom. Zoom, 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 zoom. And look what happens to the slope there. The slope is 1. It's 2. It's 1.5. It's 1.7. It's 1.9. It's 2. It's 3. What happens? Oh, it's going to get super steep. It's 4 now. Let's zoom in some more. Zoom, 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 zoom. And look what happens as I get really close. The slope now, it's up to 6. It's up to 7. What will the slope of a vertical line look like? Do you remember what that would be? Oh, yes. It's undefined. I don't have a slope once I get perpendicular, once I get to be a 90-degree angle, once I get to be a vertical line. Because, think about it, rise over run becomes... Oh, wait a minute. Let's just move you. There we go. Ah! Okay, I've kind of lost my graph here. I'm going to go back. Zoom back there. And remember that the slope of a vertical line is undefined because rise over run will run 0, and you can't divide by 0. So there would be, in fact, no slope to this thing. Let's go back to where we were back here. There we go. And let's actually graph this point now. Woo! And let's see, where are we? There we go. There it is. As I'm going this way, the slope is flatter and flatter as I go to the right. But as I go to the left, it's pretty flat. And then all of a sudden, as I round this curve, the slope goes steeply up. It goes up, and then it like disappears. It heads up towards infinity, towards an undefined infinite value. That should look familiar to you. That's like saying that -2 is an asymptote, which makes sense because -2 would be an asymptote in this equation. Because if you plugged in -2, you'd have 2 times 0, which you can't have. So that should kind of make sense to you that this blue thing here is the derivative of that. And algebraically, it's easy to see. There it is. There's our equation, 1 over 2 times the square root of x plus 2. So that's example 2. Example 3, we'll do one more, and then we'll take a look at a weird graph one. So 2 more examples. Example 3, find the derivative of the rational function. There we go. Now we got a fraction-y one. Okay, how are we going to do this one? Well, once again, we're going to have the limit as h approaches 0 of. Okay, so we have to replace these two x's by x plus h. So it's going to be x plus h plus 1 all over 3 times x plus h minus 2. Okay, so that took care of this part. Minus f of x, which is x plus 1 over 3x minus 2, all over h. See if the logic of that makes sense to you. I'm going to have to write this one kind of smaller because this one's going to take more room. So that's equal to the limit as h approaches 0 of. All right, so I'm going to just simplify that denominator a little bit there. I'm going to make that x plus h plus 1 all over 3x plus 3h minus 2 minus x plus 1 over 3x minus 2 all over h. Okay, once again, we're at this place we've been at so many times this year where we got to get rid of this denominator h. What tool in my toolbox is going to let me do that? Well, this is a fraction minus a fraction. I guess I'll have to try a common denominator. My common denominator will be this denominator times this one. So it's equal to the limit as h approaches 0 of 3x minus 2 times x plus h plus 1 minus x plus 1 times 3x plus 3h minus 2 all over 3x plus 3h minus 2 times 3x minus 2 all over h. Phew, that's a mouthful. Okay, what am I going to do with this? Well, I'm afraid I am going to have to just multiply this out. I'm going to actually have to multiply a binomial times a trinomial. Good thing I'm good at algebra. So the limit as h approaches 0 of 3x times x, 3x squared, 3x times h, 3xh, 3x times 1, 3x, minus 2 times x, minus 2x, minus 2 times h, minus 2h, minus 2 times 1, minus 2, minus, and then I have to do all of that. I'm going to do this in 2 steps so I don't mess it up. X times 3x is 3x squared. X times 3h is plus 3xh. X times negative 2 is negative 2x. And then 1 times 3x is 3x. 1 times 3h is 3h. I'm running out of room. 1 times negative 2 is negative 2. Close my bracket just in time. All over denominator. All over big denominator. Now what? Well, I don't know if you've noticed or not, but this is actually going to look much nicer in a hurry. 3x squareds minus 3x squareds, bye-bye. 3xh's minus 3xh's, bye-bye. 3x's minus 3x's, goodbye. Negative 2x's minus negative 2x's, bye-bye. And here's the only parts that don't bye-bye. Negative 2 and minus negative 2, bye-bye. But I have negative 2h minus 3h. So that's the limit as h approaches 0 of negative 5h all over. And okay, why don't, instead of dividing by this, I times by its reciprocal, which puts it right here. And if you have a hard time understanding that step, take a minute and actually do what I just said and multiply this whole thing by the reciprocal of h, and you'll see why it turns out that way. And there we go. We've accomplished our goal. Sorry, I'm off the screen. We've accomplished our goal. We have eliminated h in the denominator. So that's equal to the limit as h approaches 0 of negative 5 all over 3x plus 3h minus 2 times 3x minus 2. If I plug in 0 for h now, I won't get 0 in the denominator, so I think I'm going to do that now. So it's not a limit anymore. It's 3x minus 2 times 3x minus 2, which is negative 5 all over 3x minus 2 squared. And I don't really want that expanded. I'm very happy leaving it in that form. Your textbook's answer keys on questions like this will leave it like that too. So that's the way you should leave it. And remember, that is what f prime of x is equal to. That's the derivative. That's the equation that represents the slope of this line everywhere that x exists. Let's take a look at it on Desmos. So on Desmos, let me close this guy off. And so here was the original function. One of those guys where the 2 arms in each direction. And here is its derivative. Now think about it. What's happening to the slope here? It's super steep and it's negative. Then it sort of slows down and becomes, well, it's negative, but it's approaching 0. What's the slope doing over here? Well, the slope over here is almost 0, but it's also negative. And then it's super negative to the point where it's heading towards infinity here. Is there anywhere where this slope is positive? I don't think so. No, there isn't. Notice the slope equation is entirely below the x-axis. And if you want to see that on the other one, let's see. We got to close all this stuff. Let's see. I don't even know if this is going to work. So f of x here is going to be x plus 1 over 3x minus 2. And okay, yeah, there it is. I'm going to just take off that one. Oh, I'll leave that. I'll take off the slope equation for now. So as we move along, as this point moves along, what's the slope doing? The slope right now is so there. It's going to undefined up there. It's heading up to infinity. But as it go up there, would you? Holy, this is very hard to maneuver. This is going up to infinity, right? But as I cross to the side over here, my slope is getting closer and closer to 0. It's still negative, but it's approaching 0. Then, oops, I don't even know what I hit there. Then as I come this way, again, my slope is steeply going negative, and now it's steeply negative over there. Remember, there is a place where it wouldn't exist. The derivative would not exist. The slope would not exist at, what would it be? Negative, or sorry, at positive, x is positive 2/3, because positive 2/3 would make this 0. So here, now let's take a look at the actual equation. There's the equation again. So as my line moves along, there's what the slope is doing. Fun stuff. This takes a lot of imagination, this stuff. Speaking of imagination, wait till you see example 4. So now, example 4, it's not going to be such an easy thing to do on loose leaf. So I actually kind of going to give you a question like this. So example 4, let me just write this down. Example 4 is going to be sketch f primed given f. So this is function f. Isn't it nice? What equation makes it? Oh, I don't know. It changes direction 1, 2, 3 times. So, or actually, I guess 1, 2, 3, more like 4 times, I guess. Is it 4 times it changes direction? Excuse me. Yeah, it's an even function. I think it could be a quartic. It could be a power of 4. But, and it doesn't really matter what its equation is. We're actually just going to figure it out from a sketch. So, to make this kind of easier, I just sort of traced it as best I could. That's pretty close, eh? Onto some grid paper. You don't have to do that if you don't want to. If you really want to, you can pause the video and try to sketch this yourself. But here's what I'm going to do. I'm going to say that, okay, the slope here is 0. The slope here is 0. So I'm going to actually make myself a new grid underneath here. And I had a ruler a little while ago. Oh, there it is. So using the same Y grid, I'm going to just make a new X grid down here someplace, maybe a little closer so that you can see it better. There we go. I'm going to make an X grid here. And okay, so this is my new X grid. So just, this isn't obviously one graph. This is the same graph but further down. So what's happening to this thing? Well, okay, when x is -1, -2, I have a slope of 0. So at -1, -2, I must hit 0. Then it has a slope at +1 of, again, that's a flat part, right? Slope there would be 0, so that's another slope of 0. So it has another 0 here at 1. Then it has another 0 place where slope is 0 at 1, 2, 3, 4, 5. Looks like it's 5. 1, 2, 3, 4, 5. So it's going to hit up a 0 there. Now, what is it doing? Start thinking about what it's doing between, before, and after these dots. What is the slope doing before this dot? Well, before this dot, the slope is definitely positive, right? Think about it. All of the slopes here are going up, right? That's a positive. That's, assume I hit the line. That's a positive slope. Might even be like a +1 around there somewhere, but anyway, it's positive. It's up here. What is the slope doing between this dot and that dot? Well, it's definitely negative, right? It's negative, but it's sort of slowing down as it comes there. So it's kind of doing this. It's like going negative and then slowing down and being less negative until it gets to 0 again. Then it's positive again until I get to this 0. So again, right here would be about its steepest spot, or maybe, I don't know, let's see, maybe there? Something like that. So I'm going to make it kind of go like that. And then the slope becomes after, well, hang on a sec. After this 0, the slope is again negative, and it starts off by being really negative, but then it kind of gets even steeper. Like it starts off being slowly negative, then it gets steeper again. So I think it's going to do something like this. So there we go. That is, I think, and I don't know that I should put an arrow in there because there was no arrows in my original diagram, but there we go. Between here and here, I should kind of, I don't know, go up to about the same x value, but you get the idea. It's going to be something like that. And remember, this doesn't represent these points. It represents the slopes everywhere along these points. I stole this example from one of the textbooks that we have on the blog. Let's go to the blog for a sec. On the blog here, notice we have red textbook and blue textbook. I stole this from the red textbook. Let's open that in a new tab. And if you want to find where it is, it's in chapter 2. And it's in lesson 2.1. And there it is right there. It's actually on page 72. And you can see that they do this the same way that I do. They start by taking the picture, and ooh, they actually estimate where the slopes are 1 and -1, and then they put those points on there. And as you can see, they get basically the same picture I got. So at this point here, they say the slope is 1, so they actually put a y of 1. At this point here, they have a slope of 0, so that's where y is 0. In other words, that's the x-axis. And then there's another place where the x-axis is hit because the slope is 0. And again, over here someplace, the slope is 0. So there it is. Basically the same picture I got. Theirs is a little curvier maybe, but good enough. So you do have a few questions like this in your assignment. Please maybe check out this example in the textbook. Again, it's page 72, 73. Yeah, and then actually it's page 72. The whole thing's on page 72. Maybe go back to the blog for a sec. Those of you interested in math contests, I put an information sheet that you can download at the top of the blog. And we're updated for today. I just have to put the link for this video on there once it gets processed by YouTube. And yeah, that's about it. That's our first part of our lesson for 2.1. I'll put some more examples to 2.1 up either tomorrow or the next day. Thanks for watching.